Welcome to my live streaming. So today I'm going to talk about mostly about binary trees. It's specifically binary search trees. I think I covered binary trees in my last live stream. So today we'll focus on binary search trees. So let's go over a few of the main topics that would help us in our interview prep. So yeah, this is the agenda. So initially for some time we will just go over the definition of the binary search trees and what are the rules, like what makes a binary tree specifically qualify as a binary search tree, what are the advantages, applications, and things like that. And then we will go over a few of the core operations that are supported, like search, insert, and delete operations in the binary search tree. And then we will get to few of the basic problems. And then we will warm up, like we will solve the basic problems related to the operation supported by the binary search tree, and also we'll go to some intermediate problems, like which are more frequently asked in some of the FANG interviews and other companies interviews, and some of the little harder problems as well. So in binary search trees, the interesting thing is uh, specifically in binary search trees, not in binary trees. What are trees? To understand that trees are something which provides us a hierarchical structure for the data to arrange the data. And in the binary search tree, with that hierarchical structure, we can preserve the ordering as well. So that's the most important, or the most key, like a key thing that we need to remember. Binary search tree preserves ordering. Like whenever you insert a new element into binary search tree, we don't have to reorder or we don't have to sort it again. It will be ordered. When should we think of binary search tree? Whenever we need the elements to be ordered in one of the data structures, as in when we insert, we will think of binary search tree. Evaluate whether a given tree is a binary search tree or not. So I mentioned the rules, like all the elements on the left side, or all the nodes on the left side, should be of the value less than or equal to the current node, and all the nodes on the right side should be of the value less greater than or equal to the current node. So that would satisfy the binary search tree. So how would we evaluate it? So using let's say we can use a user to this one. Okay, I started coding here. So in the valid binary search tree, so I'm checking. I just created a recursive method here, and then I'm going through that node. And if node is equal to null, then I'm returning true. If node is greater than max value, or if it is less than min value, then I can return false. Otherwise, um, I need to validate the left node and the right node as well. So now in this case, let's say this was like I'm passing like minus infinity and plus infinity against this one. So current value is 2 and it's in between those two. So it satisfies. And then now all I have to do is I need to check the same condition for the left child. I need to check the same condition for the right child. If both of those satisfies, then I'll get true on true. If I get both of them as true, then I'll return it as true. So here the min value would become node dot, if I'm taking node dot left here, the min value will be um, the min value would remain the same for the left child. So, and the max value would become the value of the current node. And I can do the same thing for the right child in a reverse way. So for the right child, the min value will become, it will be at least of the value of the current node, and the max value would remain same as whatever its parent sent. So this is how we will solve the this is how we will validate whether it's a recursive or it's a valid BST or not. Let's check it. Okay, so base cases are passing. So one thing it would fail is whenever there is a node with value equal, that is equal to either min value or max value, then this would fail. So what we can do, let's resolve it. So now we can see here, this is, I think the min value, integer dot min value is equivalent to this one. So instead of passing integer dot min value, what we can do is we can replace this with null values to make it simple. Null is int cannot support null, so I'm converting it to integer format. And then here, rather than just checking this one, I'm checking if max not equal to null, and so if max is null, then anyway, there's no need to check this one. No need to check this one because this would be the max value. So yeah. So now let's try to compare min not equal to null. Okay. Max not equal to null. Okay. Okay. This is not a valid. Okay. Yeah. So now this one succeeds. So this checked for the validity of the binary search tree. Let's move on to the next problem. Please post if you have any questions about it. Okay, so next one is search in a binary search tree. So this is also pretty simple. So in this one, so as I mentioned, we will use the property of the binary search tree, which states that all the elements of a current node to the left of it are less than the value of the current node. All the nodes on the right side of it are greater than the value of the current node. So let's say if we use that property, how can we search? So we are searching for this particular value, and this is the root node. So what we can do is, if node is equal, if root is equal to null, then we need to return it as false. We didn't find the value. Otherwise, if root dot value is equal to val, then return true, and else if root dot val is less than current value or value of the key, if the root dot value is less than the value that we are looking for, then we need to search on the right side of this one. If root dot value is, let's say we are looking for 7 here, if the value is greater than the root node, then we need to go to the right side of this one. So if it is greater than that, then let's do the search on the right side for the same value. And if it is not neither equal nor less than, then it will be greater than. So if it is greater than the current value, if whatever we are looking for is greater than the, no, here I'm checking, if root dot value is greater than the current value that we are looking for, then we have to look on the left side. So I'm returning search BST on the left side. So we can, okay, root is equal to null, returns false. Okay, I think this one's looking good. Let's run this one. Okay, we are returning true or false here, whereas we should return root, and here also should return root if it is null. Yeah. Okay, since we are returning root here, what we can do is we can just combine these two statements, write the same one, and then it returns root. Okay, else if root dot value is less than value. Okay, yeah, let's see this one. Okay, this one works. So what if we have to do it in an iterative manner? Then let's just solve for one of this one quickly. So if we are looking at it iteratively or searching for it iteratively, let's comment out this approach. So current is equal to root. I'm just taking it in another variable because I need to modify it. Current not equal to null. I'll keep checking. And here the same condition basically. I don't have to check for do the null check here because I've checked if current not equal to null. If root dot value is equal to value, then instead of root, make it as current. Here it becomes current is equal to current dot right because I need to keep looking on the right side of this one. Here current would become current dot left. And if it comes out of the loop without finding the element, then I'll return it as false. Let's look at it. Okay. As null, return it as null. We need to return that node basically. So yeah, it's working for yeah, this works. So it's working both recursively and iteratively. So next, what's the next problem? So we are done with validating the binary search tree, which was simple, and we are done with the search in a binary search tree. Next one is insert in a binary search tree. How can we insert in a binary search tree? So whenever there is a new element, I have a tree given. So into this tree, I need to insert insert this value. In this example, value is 5. I need to insert a 5 into this tree. How can I show this one? So in this case, yeah, in this case, the value we have to insert is 5 and this is the tree given. So I'll come here in this root node to start with, which is given. So I'll compare 4 with the current node and then I'll see, I mean the node that has to be inserted, which is 5. So 4 is less than 5, then I don't want to go on the left side of this one. So I'll go on the right side of this. So now I'm comparing it with the right node here with 7. So I need to insert 5. 5 is less than 7. So I'll have to insert it on the left. I will have to go on the left side, but left side of 7 is null. There is nothing. So I'll insert it on the left side element, extending this one. So let's see how can we implement this one. If we have to implement this one, first thing is we need to find it and implement it at a proper place. Okay, let's get back to the problem. So yeah, I think we understood the approach. Here, let's see if root is equal to null, or if any value that is given itself is null, then what we need to do is we need to return by, let's create a new node using the value provided here. So okay, and then we can return this new node. Let's try to solve it recursively first, and then we can go with the iterative approach. So if root is equal to null, then we are inserting this one. If root dot value is less than the value, then what we should do? If root dot value is less than the value, then I have to insert it on the right side. Then root dot right is equal to if it's less than the value, then we are doing this. If it is greater than the value, if the root node value is greater than the value that we are looking for, then we have to insert it on the left side. So we will be modifying the left side element. Root dot left. Okay. And then we need to return the root, whatever we are inserting here. Once we do this one, let's try to run this and check. Okay, it succeeds for the base cases. Okay, it works. So let's do the same thing. Let's try the same thing using iterative approach instead of the recursive approach. So we have I copied the signature. So what we can do is let's create a new node with the value provided. And then let's go ahead here. If root is equal to null, then we need to just return a new node created. Or else what we can do is first thing is we need to iterate through the node. So in order to iterate, I'm just initializing one of the variables. So here, if I'll copy these two lines here, we don't have to do the equality check, but we need to keep iterating to find an appropriate place for this one. So if root dot value is less than value, so instead of root dot value, here it's a print value. This will be totally different. Yeah, if current dot value is less than the value, then what should we do? So whatever the current value is less than the value, then we should go to the right side of this one. So I'll modify the current as current dot right. And then if it is not less than the value, if it is greater than the value, then I'll have to insert it on the left side of that particular element. Then I move to current dot right, current dot left. So once I'm done with this one, how can I insert it? So it will go, it navigated. Let's say there's a problem given. Yeah. So in this problem, so I know this one. So we came here. There is a new node. I created a new node with the value 5. So I have the node ready to be inserted. So root is equal to null. Root is not equal to null here. So this won't be satisfied. I come here. I initialize the current as root, which is 4. And then I'm iterating until the current is not equal to null. So I'm checking here if current dot value is less than value. If current dot value is less than value, yes, it is less than value, then I'm doing current is equal to current dot write. So current became this node. And then again, I'm coming here. If current dot value is less than value, then this one. Else current is equal to current dot left. Current is equal to current dot left means current became null. So once we come out of the loop, now the value of the current is null. So I cannot insert anything. So what I need to do is I need to preserve the previous element where I need to insert as well, rather than iterating till null. But how can we do that? So I'll create another variable here, node previous, let's say, and I'll initialize it as null value. So now in this case, I'll just mark previous is equal to current. Just before we modify the current value, I'm just reassigning it to another variable. So now let's say, let's reiterate the same thing. Now current is equal to root. Current is 4, and then current is 4 here, and previous also became 4. And then here I'm checking if current dot value is less than value, then current is equal to current dot write. So current became 7 now. Now I came on another iteration here. So previous is equal to current. So previous also became 7 now. And I'm checking here. Current dot value is less than value, no. So it will come to else condition. Current value is equal to current dot left. So current value became null, but our previous stayed at 7. So we can make the new node that we created as a child node of this one, but we do not know whether it should be a right child or left child. So in order to know that, we can check this condition. If value is greater than previous dot val, if value is greater than that, then it has to be inserted as a right child. Previous dot right is equal to new node. Else, if it is not greater, if it is less than that, then previous dot left is equal to new node. So it is kind of simple. It should work. Let's see. Let's run this one. Missing return statement. And then once we are done with this, we can return root as it is. Okay, so it works for the base cases. Okay, it works. So these are like pretty simple problems, but these are the basics needed for working on any binary search tree related problems. So we need to understand how this is working, both in terms of recursion as well as in iterative method. So we don't have to remember this, or we don't have to. It's not a like memory test in the interviews. It's basically we need to understand the concepts of this, how we traverse through a binary search tree, and how the recursion method works, how it uses the stack internally, how it stores the previous state, and how we get back to the same state and everything. So now these problems, whatever we did, these are very simpler ones, but these are the basics needed to understand or solve any further complicated problems as well. Okay, Lokesh is saying something. Sure, I'll share that sheet by making it public later on, Lokesh. I'll post it as a message there. So let's move on to the next problem now. We are getting lucky that everything is getting executed on first attempt here. So next problem. So it is asking us to find the in-order successor in a binary search tree. In-order successor. So what is an in-order successor? So in the previous live stream, we had discussed 3 types of traversal. One is in-order, one is pre-order, and other one is post-order. We just have to remember the order. In order, what we do is left, current, and right. Left element first, and then current node, and then print the right node. And then in pre-order, we do is current, left and right. And then in post order, left, right and current. This is the order that we prioritize. When I say left, it doesn't mean the immediate left node, but the left subtree that is there. So that means, what do I mean by that? So what I mean here is, like, let's say if this is the tree that we are looking into in the example 2 that's given. So if I have to print a in order traversal of this one, then and this node is given as root. So I need to print left, current and right. What do I mean by that? So for this node, I came to left. Left means not just this particular node, but the left subtree, the entire overall. So I need to print this one. So in order to print this one, I'll attempt for this. So for this subtree, again, I need to print the left side of this. So left side means the entire of this tree. For this subtree, again, the left. So this is the one. For this one, there is null. So we will print 1. And then for this node, we are done with the left side subtree. After left, it's current, which is 2, 1, 2. And then for this subtree, so we are done with the left side and we will print the current one. So 1, 2, 3. So we are done with the left side, we are done with the current, and then we will print the right one. So 1, 2, 3, 4. So this subtree is done. We will move on to the main subtree. So we are done with the entire left subtree. 1, 2, 3, 4. And then we will print the current one. 1, 2, 3, 4, 5. And then we have to go on the right side. On the right side, there is only one node. So it will follow 1, 2, 3, 4, 5, 6. So if we have to print the pre-order for the same thing, for the same tree, it would be different. So in binary search tree, one thing is guaranteed is whenever there is a in-order traversal, the values will be in the ascending order, because we know that everything on the left side would be less than the value of the current node, and everything on the right tree would be greater than the value of the current node. That is the reason it will preserve the order, and whenever we do in order traversal, it will be ordered in an ascending order, as we see in this one as well. 1, 2, 3, 4, 5, 6 was printed when we did the in order traversal. But we cannot guarantee the same properties for pre-order and post-order traversals. If we see pre-order, it's current, left and right. So for this one, current is 5. So 5 will be printed first and then the left subtree. So for this one, current will be printed first, which is 3, 5, 3, and then it will go to the left side. So for this one again, current will be printed first and then it will go on to the left side. For this one, current will be printed and then left one. So it will be like 5, 3, 2, 1, and then there is no right for this right child for this one. We are done with the current and left. So there's no right child, so it will go on here. So this one, current and left are done. So 4 should be printed. So it is 5, 3, 2, 1, and then 4. And then it will come here. So for 5, current is done and entire left is done. So it will go to right. So it is 5, 3, 2, 1, 4, 6. So no order is preserved in the pre-order. Same way the post order, it's the reverse order. It is left, right, and then current. So yeah, those are the traversal. Those are like like I have spoken in detail about traversals and different techniques in my previous live stream. But if you have any questions about it, feel free to post it in the comments there. So let's see how can we go about it. So this is whatever they have given. They're asking in order successor in a binary search tree. In order successor in a binary search tree. So how can we do that? Let's say if it was a binary tree, then it would have been much more difficult for us, thinking that there would have been various different scenarios. But in a binary tree, we can follow it, we can solve it using the binary search tree properties pretty easily. So let's see, successor means the next element. Basically, the successor of 5 here is very straightforward, which is 6. The successor of 3 could be 4. And here the successor of 6 is being asked. So after 6 there is nothing. So the successor of 6 is null. In this tree, the successor of 1 is, so this is a different case. So for 1 there is no right child. So the successor, like if we are traversing as an in order, so this is like the current node. For the current node we will go to left first and then left and then current and then right. So 1, 2, 3. So successor of 1 would be 2, which is its parent. So how can we tackle this one and solve this. Let's say, so I haven't seen this problem, but there can be multiple scenarios. Like when there is a right child, then it's quite easy for us. Like the leftmost child of the or leftmost element of the right child, basically. So this is a straightforward case 4. Let's say this was a 300 and this was 400, and then what if there was 350, 375 and all? So that would have been inserted here, like after 375 is greater than 300, so but it is less than 400, so that would have been inserted as a left child here, 375. So that would have become a successor of 300, but uh, but that's not the immediate right child. Immediate right child would have been 400. So 375 would have been the left element of this one. So what we need to do is we need to go to the leftmost element of this line, of this lane, leftmost element of the right child of any node, if there is a right child. Otherwise, how can we go to the parent? That is a bit of the tricky scenario. If there is a right child, then it is easy scenario. We can work it out. If there is no right child, then it gets a little trickier. So how can we solve this case? Let's see. So in this one, what we can do is, so all I can think of is we need to keep traversing in the same way. Let's see if let's take another node as we usually take and assign root to this one, and then while current not equal to null, we need to check for this case. Like if p is the node that is given, if p dot value, that would be, if current dot val is less than or equal to p dot value, if current is less than or equal to p dot value, then we need to move on the right side. So if current value is less, that means if current value is less, if we need to keep moving on the right side of this tree. So current is equal to current dot right, else we'll move on to current dot left. So when would we encounter a successor here while moving? So for the current one, let's initiate the successor as, like, if we keep moving on the right side, and if we do not, and if the final right child doesn't have any more right, let's say, let's assume this tree node, whatever, I hope it is visible. So yeah, let's assume this tree node. So in this case, basically what's happening is, so if we are looking to, okay, we are looking for a successor of 6. So we are looking for a successor of 6. So what will happen is, I'm checking with I initiated the current node as 5, and then I need to, I'm checking here, while current is not null, then I'm traversing. If current dot value is less than or equal to p dot value is 6. If it is less, then I do current is equal to current dot right. Current is equal to current dot right. I came here, and then again the same thing. If current dot value is less than or equal to p dot value, current dot value is less than or equal to p dot value. Yes, that's correct. If it is less than or equal to this one, then again current is equal to current dot write, which is null. So there is nothing that is a successor of this particular value in this tree. Successor means there is no value after this 6. So we do not get anything. So we have to return it as null. So what we can do is, in this case it works, but let's say for this case. So I've come here, I initiated current value as 2 for this case. So now I need to check, I'm looking for p is equal to 1. So if current value is less than or equal to p dot value, no, it's not less, it is greater than 1, 2 is greater than 1. So I'll come to else. So current, I'm doing current is equal to current dot left. So current is equal to current dot left. So I came here 1. So now here I'm checking again if current dot value is less than or equal to p dot value. Yes, it is equal to p dot value. Then I'm doing current is equal to current dot right. So there is nothing on the right. Again, it will go to null. So I need to preserve the successor of this one somehow. So the successor of this one would be every time I move to the right side, is the successor possible? So there is, let's take it as one of the node here. The node successor is equal, I'll initiate it as null. So for me, as I keep moving on to the right side, is there a successor possible? So assume this example 6. So I encountered a 5 here. So 5 is less than 6. Could this be a probable successor of 6? No, right? Successor means the value after this one. And we know from binary search tree properties that it is always in the in order. Successor means it's always in sorted order. So whatever the value is, it should be greater than the value given. That would be the successor. So 5 can never be a successor of 6. So I won't do anything with 5. But at the same time here, I encountered 2 here for 1. So when I'm looking for a successor of 1, can 2 be a successor of 1? Possible. What if there was 1.5? So we cannot be sure of that one. So we cannot return it here. There could be a 1.5. So let's say I came on the, so 2 is greater than whatever the value we are looking the successor for. So we came here. So we came here 1. And then while coming here, before assigning it as, before searching on the left side, what I can do is I can mark that as one of the probable successor. So while moving only on the left side, while moving on the right side, I don't want to mark it as a probable successor or a possible successor, because when we are moving on the right side, that means the current value is less than the value we are looking for, and the value which is lesser than the value we are looking for, that cannot be a probable successor. But if a value is greater than the value we are looking for, that could be a probable successor for that value. That's why I'm just assigning that value. And this doesn't have to be a final successor. Let's say, let's explain with another example here. Let's say if, let's say here, in this case, in this tree, in the bigger tree, if we are looking for a successor of 2, or let's say we are looking for a successor of 3. Okay, so now we came here for 5. I'm checking 5 is the current value, and if 5 is value, so if 5 is less than or equal to 3, no, it's not less than or equal to 3. So I came here and marked successor as current, which is 5. So now successor is equal to 5, and then current is equal to 3. Now current became 3, and then okay, current I came here. So now while current not equal to null, if current dot value is less than or equal to p dot value, current dot value is less than or equal to p dot value. You mean 3 is less than or equal to 3? Yes, that's correct. So I marked current is equal to current dot right. Current became current dot right. So current became 4. Sorry, here current became 4. I'll just erase this here. Current became 4. Okay, once that is done, okay, once that is done, so I'm again checking. I'm coming back again here, and the value I'm looking for here, uh, current dot value, which is 3, is it less than or equal to, yes, current dot value is 4, is it less than or equal to p dot value? No, it is greater than that. So what I can do is, okay, that could be a probable successor as well if that is greater than the current value. And we know that that would be less than this. So I'm marking it as 4 because we are coming on the left side means it would be less than whatever we saw previously. So current value became 4 and current is equal to current dot left, which is equal to null. So current became null again. So current became null. So we will come out of the loop and we can just return the successor, the last probable successor that we thought in the loop. So when we go to the left side, then only we will think the current value can be a probable successor. When we move on to the right side, we won't think that would be a probable successor because this value is anyway less than the value that we are looking for. So this can never be a probable successor. So that's the thinking here. Let's run it and see if it passes all the scenarios. Okay, let me clear these example specific comments. Okay, so this is submitted. So this one works. As I said, this is using the binary search tree properties because we know that in order successor of binary search tree, they have asked specifically, we know the properties here. So here we knew that if we are moving on to the right side, there can't be a probable successor here because the value would be greater than what we saw there. That's why we did not mark it like that. So this is where we have used the binary search tree properties. If it was not a binary search tree, then it would have been little more complicated for us. Then we should have addressed what if the successor lies in the right side of the tree, and what if there's no right child, and what if there are both the childs, and like if we need to find it in the parent, and all those scenarios and all those cases. Let's say if there was a child here, like 3.75 or something, then its immediate parent can't be its successor. Then it has to be 3, which is or 3, or yeah, there could be various different scenarios. We can tackle it in maybe another session or in the end of this session itself. But yeah, this one for binary search tree, we have used the property and it works. Let's move on to the next problem. Let me see. Lokesh has a question here. Could you please share the sheet after the streaming? Yes. Can't we store the in-order traversal in a list and print the next of P? Yes, Lokesh, absolutely. Let's see. Yeah, that's a very good question. So we could have printed the in-order in a tree. In-order traversal in a list entirely, and we could have just printed the next one after 6 or after 1 or whatever. But what's the downside of that one? In order to do the in order traversal, basically we will use O of n. If we need to do in order traversal, like we need to traverse the entire tree, so that would be a O of n operation. And what if we just find the number? Then we could have stopped as well. If we just find the number, yeah, if we find the number, then we cannot stop in between the recursion. But yeah, as you asked, like if we print the in-order traversal, then it would be O of n. And then among that one, we will find maybe using binary search or anything that could be best case O of n log n, sorry, O of log n. And we will return the next element or immediate next element after that. But as opposed to that, here, all we are doing is we are trying to get to the particular value. So you can see here, my traversals, I am doing either current dot right or current dot left. So with every traversal, I'm probably eliminating half of the tree, like given the condition that the trees are balanced. If trees are not balanced, then it's not efficient. I agree. It's as same as any array or linked list. But if the trees are balanced, I'm removing half the sample space here. So I'm just searching for half of the elements. Again, next step, I'm removing the half. Again, next step, I'm removing the half. So it would take O of log n for me for this operation. Whereas in order to print and do that, so that would be O of n. That's the difference. I hope that was clear. So let's go back to our sheet here. Yeah. So now we are done with the in order successor. So let's see the delete operation. That's the primary operation. So we are done with the search and we are done with the insert. So now delete operation. This is a little more complicated than the search and insert operations, mainly because we can see here. Yeah. So in the delete operation, you can see here. So there is an example given. Um, this is a tree and they are asking me to delete 3. What if we delete 3 here, like there is a conflict. Which one should be replacing 3? There is a probability that, okay, 2 can replace 3 here and 4 can replace 3 here. So what if 2 replaces 3? Even then also it would be a valid binary search tree, right? Like there 2 is less than 5, it's here, and 4 is greater than 2, which would be a right child of this. So here they have given, okay, it would be reduced to 5 and then 4 would be replacing 3. Okay, that is also a valid scenario. And then another example given here, given a key to delete is, okay, they have just explained it. So we find the node with value 3 and delete it. One valid answer is 5462 shown in, please notice that other valid answer is 526, 526 null. Okay, so it could have been like if 2 replace this one, then it would be 526 4 null null 447. So yeah, irrespective, we can go with one of those approaches. So what's the next question here? Next example given is there is a tree definition given and then there is a key given as 0 which doesn't exist in this particular tree. So the tree does not contain the node with value 0. So we do nothing and we will just return it as it is. And then root is null and key is 0 and we do not do anything. We will just return null as it is. So the first thing in this example what we saw. So in order to delete a value 3 from this tree, first thing is we need to find 3. So that is a O of h or O of height or O of, in the best case, O of log n operation as we discussed. So how do we find 3 and what should we do after finding 3? After finding 3, can we replace this by 4 directly? Is that the only case that is possible? And I would say no. First thing is, let's say if we wanted to delete 4 from this case, from this example, not 3, if we wanted to delete 4, then 4 doesn't have a left child or 4 doesn't even have a right child also, then we could have just made 3 dot right is equal to null and nothing else. Then it would have worked, right? So if there is no, if a node that we are looking to delete doesn't have a left child or node right child, then we can just make it as null. That would work. But if it has only one of the child, let's say we are looking to delete which has one child, which we are looking to delete 6 from this example. So if we wanted to delete 6 from this example, it doesn't have a left child, it just has only one child. Even if it has just left child and there's no right child, then also it would have been the same approach. So now if it has only one child, then we can replace this with this child. Like we can connect 7 to 7 as the right child of 5 and 6 would be nothing. Like right child of 5 would be 7 means 6 would be null. So that would have deleted as well. So now we covered the scenario when it has no child and when it has one child. What if it has two children? So if it has both left child and right child, what we need to do is we can select this one, either leftmost element on the right child. leftmost element on the right child. Please carefully uh, concentrate in this one. So leftmost element of the right child means, as I said, so I'm not sure if I have the example for that one. Yeah, let me share this problem. Okay, so now if I want to delete, observe this tree. If I want to delete 5 from this, no, 5 from this here. So either 5 could have been replaced by, like, whatever the approach we are following here. Can 4 replace 5 here? No. If 4 replaces 5, where would 3 go? There is a conflict, right? So what I said before, leftmost element of the right child. So what is 5's right child? 5's right child is 4, and leftmost element of the right child means keep traversing to the left of the right child. So there is 3. Let's say there was like 3.5, sorry, there was like something 2.5 or something. Uh, even even that was okay. Sorry, this is not a valid tree itself. I'm giving a wrong example because I'm saying this, 4 is on the right side of 5. So that could have been a wrong example. So let's see with this one. This is a valid binary search tree. In this one, if I want to delete, there are no very good cases for me here to say. Let me add a case here. Similarly, 5, 3, 6. Okay, so now okay, okay. Now if let's say if we wanted to delete 3, then we cannot just replace 3 with 5 because 5 has another child. So the best thing that we can do is we can replace the leftmost element of the right child. Replace this with the leftmost element of the right child means right child is 5, its leftmost element is 4. Let's say if there was a 4 point something like a 3.5, then that also we will add something like this, right? Let's assume that's not an integer tree. Then we would have a 3.5 also here if we wanted to add, because we come to insert 3.5, it is less than 6, we come here, it is greater than 3, we come here, it is less than 5, okay, it is less than 4 on the left, so I kept coming here and 3.5. So now the best case to delete 3 is leftmost element of the right child. Right child is 5 and its leftmost element is this 3.5. We'll replace this 3 with this 3.5 with this value, and then this one should be deleted. This value should be deleted. So we will just eliminate this particular thing from the node. So that means we deleted the 3 from this tree, and yeah, and then we preserved the rule of the binary search tree as well. So now also you can see 3.3.5 is less than 6, so it is on the left side. 5 is greater than 3.5, so it is on the right child, and 4 is less than 5, so it is on the left child, and every element in here is less than 6. So yeah, so the binary search tree property is also preserved, and we were able to delete 3 as well. So we saw three different scenarios. When there are two childs, when there is one child, and there are when there are no child. How can we go about deleting it? So let's get to the coding part. So what I said, before we delete any node, first thing is we need to find the node which we need to delete. So in order to do that, let's see. First thing is if root is equal to null, then we can just return null. And if root dot value is less than key, if root dot value is less than key, then what should we do? If root dot value is less than key, let's say we are asked to delete 6 here, and if root dot value is less than 6, then we need to move our search space to the right side of this one. So left side of a tree can be discarded. So what we can do is root dot right is equal to, we can call the same method on the root dot right. So once we delete, that should be preserved. Okay, so I'm not just calling delete method. So if I just call delete method, that would return just the delete, just whatever the delete function returns. So now I'm assigning that to the right child. So after we delete it, whatever the node will result here, so I'm assigning that to the right child here. We could have been asked to, we thought we are asked to delete 6, right? So whatever the element is replaced from 6, that would become root dot right. So in the same way here, else, if root dot value is great, let's do else if. When it is equal, we need to go ahead with deleting. So if root dot value is greater than key, then we need to move our search space to the left side. So what we can do is we can just copy the same thing, and root dot left would become, okay, here I didn't pass root dot right, so this would be root dot right, and here I'll pass root dot left. So delete node of root dot left and find for the same key. So we keep traversing until we find the key using this. And then once we find this one, so if it is not less than or if it's not greater than that, then that means it is equal to the key we are searching for. Then we have to delete that particular node. How can we delete that node? So first thing is, if I'm checking the case, three cases as we saw, if the node to be deleted doesn't have children, and if the node to be deleted has only one child, has both children, both child, or whatever, both child. So yeah, this is kind of implicit. If the node to be deleted, we are looking for that only. Yeah, doesn't have children, one child, both child. Okay, this is the easy case. Let's handle that one first. If root dot left not equal to null, so root is the one which we need to delete now. We figured out that. And root dot right not equal to null. If both are left child and right child both are not there, then what we can do is we can just return null. Not return null. Here what should we do? Yeah, we can just return null. Nothing like. So the root would become null in that case. Like root is the one which we need to delete. So if it doesn't have a left child, if it doesn't have the right child, I can just return null. Here, let's check another case. Else if root dot left okay, here I have to check if root dot left is equal to null and root dot right is equal to null. I was checking the reverse. If root dot left is equal to null and root dot right is equal to null, if both are null, then I'm returning null. if it has only one child, then it will satisfy. Like I have already checked for the above case, right? So yeah, so I have already checked if both doesn't have a child, both side, if left is also not there, right is also not there, then I'm returning null. Now here I'm checking if either of them, one of them is null, then what I need to do. Then all I can do is if one of them is null, then I can replace root is equal to what I can do if root dot like if the root dot left is null, if root dot left is equal to null, then what I can do. So I'll explain it in detail. So I know that one of them is null. If root dot left is equal to null, then root will become is equal to root dot right. If root dot left is not null, then that means root dot right is null. Then what I'll do, root is equal to root dot left. So this would work. Yeah, I'll try to simplify it. I use ternary operators in these cases where I'll write it like this. Root is equal to, if root dot left is null, then root is equal to, I have already have, then if root dot left is null, then root is equal to root dot right, else root is equal to root dot left. Okay, so let me take out this one. So okay, so now I checked if it doesn't have both children, else if it has only one children, else that means it has both the children. This is the trickier case. If it has both the children, then I know that it has left child and right child both. So what I'm doing here is, in this case, so as I said, if I wanted to delete any case, like I need to check the leftmost element of the right child. So let me take the right child here, root dot right, and then let's initiate another one, leftmost of right. I'll initiate that as right child first, and then while, okay, I'm checking leftmost dot left not equal to null. I'm traversing to the leftmost of left not equal to null. Dot left also I'm checking. I'm not just checking leftmost of right is equal not equal to null. I'm checking if leftmost of right dot left not equal to null. If that is the case, leftmost of right is equal to leftmost of right dot left. So I keep traversing. Basically, let me go back to that case. So here I had 3.5 here, right? And this is the right, this was the right child. As long as there are left elements, I was going to this one. So it was in originally in this case, this state. So there was a 3 here, and there was a 3.5, and there could be a 3.75 also. Let's add. Yeah, there can be a 3.7 here. So this could be a right child, but I don't want this one. For 3, immediate next successor is 3.5, not 3.75. So I'll replace this one with this one. Exactly like we found the in-order successor in the previous problem, right? I'm just replacing this with the in-order successor, which is 3.5. So the leftmost element of the right child means I initiated with as right child, and then I kept until the value dot left is not equal to null. So this value dot left equal to null, right? For this element dot left is null. So I'll stop at this one. So this is the element I'm going to replace. I got that one. So let's get back the code. So now I got the element that I want to replace the current element with. So what I'll do is now root dot value is equal to, I'll replace it with leftmost of right dot value. After that, I need to delete the current root also. So what I'll do, not the current root, I need to delete that leftmost of right value. Basically, I need to delete once I do this. Let's go back here. Once I eliminate 3.5, uh, basically once I replace 3.5, I need to delete this 3.5. So I'll call the recursive function again on the right tree here. So on this right tree, if I call a recursive function to delete 3.5 now, so what it will do, it will just keep traversing. 3.5 is not this one, 3.5 is not this one. Okay, this is 3.5. I need to delete this one. It has only one child. What it will do, it will replace 3.5 with this one child. So this will become 3.7, and then this will be null. So that case was already handled in the previous version. So this will become 3.7, and then this entire thing would be deleted. So this would be the resulting, sorry, this one already replaced, right? So this one, if I replace 3.5, yeah, and this one becomes 3.7. So that would be the case, final output. So let's go back to that one and code for that scenario. So root dot value I replaced. Once I replace the root dot value, I need to delete the other one. Root is equal to, I'll delete the, how to delete it, I'll call the recursive method again. Delete of root dot, it is on the right child of this one, right side, and then not the key, but the value of that node to be deleted has this value, leftmost of right dot value, this value. So I'll delete that one. Once I am done with all this, I'll have to return root as it is. So I'm returning the same tree definition here. So yeah, so let's run this one. Might be some bugs, we can fix it, but yeah. Okay, here we can see 5 comma null comma 6. So okay, 3 has to be deleted. Here this tree is given and 3 has to be deleted. 3 has only one child. If 3 has only one child, then what should we do? And I'm giving 5, 6, 7. 3 is replaced as null in this case. So you can see, yeah, just 5.6.7 is the output I'm giving. Expected is this one. So 3 has both the children, right? 3 has both the children. So it will come to this case. 3 has both the children. The right child will become root dot right, and leftmost of right is right child. Leftmost of right dot left not equal to null. Okay, leftmost of right, okay, not equal to null, then that's the case. Root dot value will become leftmost of right dot value, and then root dot delete. Okay, this one will be, after deleting, it would be assigned to root dot right, not to the root. It would be assigned to root dot right. Root is already, root dot value is the leftmost value. So in this case, one of the mistakes at least I'm doing is, after replacing 3 with 4, which is the next value, what I'm doing is I'm replacing this with the value that comes from deleting this node. So here I replaced in this line, what I'm doing is root dot value is equal to leftmost of right. Leftmost of right is 4. So root dot value became 4. Okay. Once that is done, I should modify the root dot right after deleting the node, deleting the leftmost of right value. So it could be here or it could be somewhere in this hierarchy. But what I did was root is equal to delete node. So this, once it deletes, once it returns null, this entire thing became null. So I now I made it as just root.write is equal to delete node. So let's run this one and see. Okay, now you can see once I delete this, like I have to delete 3, I replace 3 by 4 here. After that, 4 retained that place, and now it works. Let's submit this. Okay, so this one works. Awesome. So this is one of the not so easy problem or easy operation while talking about binary search tree. Let's go to the next one. So before going to the next section, let's take a quick break. But if you have any questions in the meantime, I can address those things. So feel free to post it in the comments. And if you have any other problems other than what is there in this agenda, feel free to ask me. I'll try to share this one by making it public in the comment section. Thank you. Let's meet after the break. Okay, let's get back to the problem now. Thank you for waiting. So, yeah, let me share my screen. Yeah. So here, in this one, like we have in this section, intermediate problems, I'm going to solve 3 more problems. These are also like kind of LeetCode medium-ish, I guess. Yeah. Yeah. All of those are like one of them is easy and other ones are LeetCode medium. So let's see. For the case smallest integer, let's start with this one only. Case smallest integer. lowest common ancestor and convert sorted array to binary search tree. So for the kth smallest integer, let's see. So there are a couple of ways with which we can solve. I mean, iterative and recursive. Let's like whenever there is a traversal, it's always easy to go in the recursive approach. Let's solve it using recursive, and then we can discuss the drawbacks of that approach. So let's keep it in a list. Let's traverse recursively, and then let's keep that value in the list. Let's do it like this one way. Okay, and so I just created a method called in-order traversal, and then tree node. We can keep it as any node here. And yeah, in-order traversal means, as we discussed, left, current, and then right. So first thing is, let's do sanity check here. If node is null, then we can just return without doing anything. Otherwise, left. First thing is, let's move on to traverse on the left child, node dot left, and then the current one we need to add it to the list or the output that we define, in order dot add node dot val. And then what we can do, we need to handle the right child. Okay, so this one's done. So we will have the elements in the in order in this in order list. After that, what we can do is return so kth smallest element. So first element, so as we discussed in a binary search tree, it will be sorted in the ascending order if we do in order traversal. So they are asking for the kth smallest element. So 0th element will be the like whatever will be in the 0th index will be the first smallest element. Kth smallest element will be in k minus 1. So what we can do is in order list dot get k minus 1. Let's see if this works. Okay. Oh, I didn't make this public intentionally, location. So this one doesn't have to be. So I'm just accessing within this. This is the method which is exposed as public. Oh, the notion you are saying. Okay, so this one's working now. Yeah, so let me address that after this problem. So this one, um, uh, one of you had asked a very good question in previous one. Why didn't we just take the in-order traversal and then find the successor? In the same way, in there, like we could have easily reduced our search space to log n, but here we are not even reducing the search space to log n. So kth element means I'm just taking all the elements in the in order list, and then I'm just finding the k elements. Why didn't I stop it at k? So it was not the recursion was not in my control when we went to the minimum element, and from there we started. So what we can do is, instead of having this uncontrollable recursion using the uh, using this method, recursive method, what we can do is, so that would be like calculating all the elements, uh, calculating all the in order list without any use. So we could have stopped when we got the kth element only. How we can do that? We can do that by, let me Let's code that one. Another approach, I'm just copying the signature here. Let's comment out this code. We copied the signature here, and then if we simulate the same thing, same recursion using the stack, then we can simulate it locally. Let's say how we can do it. So here we need to traverse to the minimum element and then take it one by one out of the stack. So what I can do is, well, like we can keep executing it until we find the first k elements. So in order to go about that, while root not equal to null, I'll keep appending it to the stack. Stack dot push. I'll keep appending the root to the stack, and then root is equal to root dot left. So the current element. So let's what it will do is, let's go back to the example here. So in this case, so the third smallest element is 1, 2, 3. That is the one. We returned it. How did we return it? So first thing is I came to 5 here. This is not the smallest element. And then I pushed it to the stack. And then I came to the left, root dot left, and then 3. And then that is not the smallest element. I came to the left. I pushed 3 to the stack. And then I pushed 2 to the stack and 1 to the stack. So then root is equal to root dot left, which became null. So I come out of this loop. Once I come out of this loop, what I can do is I can pop the first element from the stack. So first element of the stack, when I pop, it won't be 5, it will be 1, because it will be in the reverse order, last in first out. So 1. What I'll do after that, if k is equal to 0, then I'll return root. If k value becomes 0, then I can return the root. Like let's say if they had asked the smallest element in this one, I mean zeroth smallest, or zeroth smallest element, 1, 2, 3. Yeah, if k is equal to 1, I guess. I think if k is equal to 1, then I could have returned this as root. But they haven't asked for k is equal to 1. So what I should do, with every step here, k minus minus, I can do k minus minus, and then I need to process root dot right also. So how can I process root dot right? So all those elements are processed by something like this. So now I pop the left elements. Okay, now this one is done, and then it will come back here, the second element, and then third element. Let's say if the k was 4 here, then I should have k was 4, or let's say k was 5. What if that was the case? If k was 5, then, and if I left it as it is, yeah, then I have 5, 3, 2, 1 in the stack. So 1 is already popped, and k value became 4. Okay, if k was 5, I'm checking if k was 5. K minus minus, k became 4. Okay, now I came here, root not equal to, what I can do, root not equal to null as of now. So root should become null when I come back here. So in order to do that, I can do root is equal to root dot right. So when I do root is equal to root dot right, so 1 dot right, which is equal to null. So now again, root became null. So root became null, so I won't come inside this loop. So what I'll do is root is equal to stack dot pop again. Stack dot pop, when I do, the next element 1 is already popped, so I popped 2 here. So root became 2, and then if k is equal to 1, no, k is equal to 4, I can't return 2. So I came here and reduce k to 3. And root is equal to root dot right, which is null again. Again, root is null, so I won't go inside this. Root is equal to stack dot pop, which is 3. And then what I do, um, k is not equal to 1, so I won't return it. And then I'll reduce this to 2. And then root is equal to root dot right. Here, root dot right is not null. I'll assign root dot right as 4. So root dot right is 4. And then I come back here. Root is not null. So stack dot push of root. So I pushed 4 to the queue. And then here again I'm doing root is equal to stack dot pop. 4, like when I popped, 4 would be popped. And then k is equal to 1. No, not yet. And then I reduce k is equal to 1 here. And root is equal to root dot right. Root dot right is null. So now the next thing is root is not equal to null again. Root is equal to null again. So root is equal to stack dot pop. So 3 was popped, 4 was also popped. So stack dot pop would return 5 here. So now root is equal to 5. And then is k is equal to 1? Yes, k is equal to 1. And I return this node itself. This is the fifth smallest element. 1, 2, 3, 4, 5. That's how it works. So in the same way, like I just took fifth smallest element because if I had taken 3, there was no chance for me to explain this root dot right. It would have just went to the left and then popped 1, 2, 3 and returned 3. If it was fourth element, then it would have come to this one. Fifth element is 5. It will go in the same order. If I take it as right, it would have assigned again root is equal to root dot right, sixth element, and then it would have come and pushed 6 to the stack here, and root became k is equal to 1 after this one, and then it would have returned 6. So if you have any questions in this one, please post it. So in this approach is better than this recursive approach in a way that I haven't processed all the elements. Like let's say if the left tree has at least, like if it's a balanced tree, then I have processed only half of the tree because I'm just dealing with the left side of the tree. And what if it is a skewed towards right? Then I would have saved a lot of traversal time here. So this would this is much more improved version than using this one. In asymptotic analysis, asymptotic notation, the worst case for both of them are same, but this would save iterating through all the elements in the array or all the elements in the tree. So let's run this and see. Return root dot value here. It's in the, they are not asking for the node, they are asking for the value. Okay, so this works. Okay, so the next problem is lowest common ancestor of a binary search tree. So this is like this problem I think we had seen for the binary tree as well. And this binary search tree, usually whenever some question is asked for binary tree, it is more generic, and we do not have this property of all the left side elements are less than the current node and all the right side elements are greater than the current node also. So that's an additional property in binary search tree. So usually we can use that property and solve the same problems much more easily in binary search tree rather than in binary tree. This problem, for reference, let's solve it using binary search tree property first. So now lowest common ancestor of a binary search tree they have asked here. So for that one, let's see what's the solution. So in this one, I think it's pretty easy. So what we can do, lowest common ancestor. So here, yeah, let's take the example here. So P is 2 and Q is 8. P is 2 here and Q is 8. Lowest common ancestor is, okay, both are on the left and right node. So 6 is the lowest common ancestor. This is easy. I mean, from the looks of it as well. Let's say P is equal to 2 and Q is equal to 4. 2 and 4. In this, the lowest common ancestor is 2, right? Like, I mean, it's inclusive of the element. So both we can get both of those elements when we traverse the subtree of this node. So that is the one. So in any tree, what we can do is, like, let's say we started our traversal from here. If both the elements are less than this value, then I'll have to move to uh, move and look for the lowest common ancestor on the left side of this element. And if both the elements are greater than this one, then I have to look for lowest common ancestor on the right side of the element. So what if the left side immediately as soon as we move the element exists? Then in this case, as we saw, like those elements will be in the same hierarchical structure, and we would be returning one of those nodes only, which is 2. Like we when we were looking for the lowest common ancestor of 2 and 4, we just return 2, the element itself. In the same way, if we were looking for lowest common ancestor of 8 and 7, let's say, then 8 and 7 both are greater than 6, so we move to the right element. And here we saw that, okay, both are not less than 8, or both are neither less than greater than 8. So one of them is equal to 8, right? So both those conditions fails, and I can return the current node itself. What if we were looking for the lowest common ancestor of 7 and 9? In that case also, 7 is less than 8, but 9 is greater than 8. Both are neither smaller, both are neither greater than 8. So I can return 8. What if I was looking for something like lowest common ancestor of 3, 3 and 4? So now at 6, both are smaller than 3 and 4. So, sorry, both 3 and 4 are smaller than 6. So I move to the left side. And both 3 and 4 are greater than 2. So I'll have to move to the right side now. And 3 and 4 both are neither smaller nor greater. I mean, 4 is neither smaller or greater than 4. So I'll return this node only. So that's the rule we will follow. So let's check now. If uh, the same way, root dot value is greater than p dot value, and root dot value is greater than q dot value, then what I should do? If root value is greater, then I should move on to the left side. Then I'll do the same thing here. Root dot, I'm looking for the same thing on the root dot left. And what if both are root dot value is less than p dot value, and root dot value is less than q dot value, both. So if root was less than both, then I would move on the right side. So what I'll do is I'll call the same same recursive method on the root dot right. And if both of these doesn't satisfy, then that means either this itself is one of the node, or both are on the either side, means this would be the lowest common ancestor. So what I can do is I can just return the current node if both condition doesn't satisfy. Let's run this and check. Okay, here I need to return these. Okay. Okay. Using binary search tree, it kind of makes it very easier for us for finding the lowest common ancestor, because we can make the decision based on the value is greater or value is lesser. But what if we do not know the value and move to the left side or the right side? So that's when it gets complicated. So there is a problem for binary tree also. Like, let me look it up. Lowest common ancestor of not binary search tree, but just a binary tree. So that one we had solved in one of the live streams, I think. But let me solve it once again. That is also one of the frequently asked question. So let me take a stab at it. Okay, here lowest common ancestor of two elements again. So in this case, what we need to do is, yeah, here we do not have that relationship that all the left side elements are less than 3 or all the right side elements are greater than 3, because this is, we are solving for a binary tree, not a binary search tree. Again, clarifying this, whatever the problem we solved here, lowest common ancestor of a binary search tree, that is 235, and now we are solving 236, which is lowest common ancestor of binary tree in general, and we cannot use these properties of less than the root value and greater than the root value, because it's not guaranteed in a binary tree. It's guaranteed only in binary search tree. So what we will do in this case, we can do two things. Like, let's see, first thing is, let's create a, I have it fresh in mind since I had solved this in one of the live streams. So here, I'm not, let's start from here. I think we need to just do Boolean. Yeah. And let's take this as a node. And then here, what I'm doing is, what we need to do is, basically first thing is, if both of them are, in case if node is equal to null, then return false, first thing. And then if I need to check, so I need to check on the left tree if there is, if one of those element exists, or the either P or Q, and I need to check on the right tree either of those element exists. If that doesn't exist, and I need to check with the current value, if current value is equivalent to one of those value, and if that, like, based on that we will make the decision. So let's get those things. So here what I'm doing is, so node dot left, and then this should give 1 point, like either one of them should exist in order to return true, like either P should exist or Q should exist, or the current node itself should be equal to P or Q. So let me initiate it as int present on left. If present on left, if this one returns true, then I'll assign this as 1 point, otherwise it is 0. And then I'll do the same thing, present on right. If it is present on right, then I'll return 1, or else I'll return 0. And in present in current. So in current, how I'll check this one? In current, node itself is equal to P, or node itself is equal to Q. In order to make it more readable, let's add parenthesis. If either node is equal to P or node is equal to Q, then I'll return 1 or 0. So now the total of this one should be equal to at least 1 in order to return true. So return plus should be greater than or equal to 1. So then I'll return it as true. Okay, so now it returns as true. So okay, now I came here, I'm looking for 5 and 1, common ancestor of 5 and 1. So in this node, I'm checking for on the left node, like first thing I came on lowest common ancestor recursive node dot left. On the node dot left here, I came here, and then for this one I'm checking again lowest common ancestor on node.left, so it will come here. On 6 again I'm checking common ancestor of node.left, which is null, and it returns as false. And for 6 left is false, and for 6 right is also false, which is null, it returns false. And current present in current node is equal to p, 6 is not equal to 5 and 6 is not equal to 1, neither equal to 5 nor equal to 1. So all three become 0 0 0. 0 plus 0 plus 0 is not greater than or equal to 1, so I return false for 6. And then here for 5 I evaluated 6, the left child, and then present on right, I need to check present on right. Present on right for that one, so for 2 again, for 2 I'll go left 7, again null null 0 0, and 7 is not neither equal to 5 or 1, so 0, so returns false. And 4 again, for 4 null null return, and 4 is neither equal to 5 or 1, for 4 also it returns for false. So for 7 and 4 both return false, and then 2 is neither equivalent to both of those, so left and right false, and current is also false for 2, so this one also will return false because this is 0. And again coming to 5, so the left is false and then the right is false. Left is 0, I mean right is 0. Both are assigned as 0. And current is node equivalent to P. Yes, node is equivalent to P, which is 5. And node is not equal to Q, but it's okay. We have a OR condition here. Node is equal to P. Then we just assign 1 here. And then this one will become present on left plus present on right plus present in current is greater than equal to 1. It's equal to 1, right? So I'll return it as true. So I return true for this one. So for 3, I checked on the left, which is true. I checked on the right now. I'll check on the right. In this right, the same evaluation all happens. For 0, it returns false. For 8, it returns false. For 1, left is false, right is false. So for 1 itself, the current is itself is true because node equal to Q, so that's satisfied. So for 1 it is true. And then if it comes to this case, like if it comes to the root node here, so left is true, right is true, left is true and right is true, so 1 and 1, so it will become 2. So what I can do is I can write another line here. If the same thing, if this one rather than greater than or equal to 1, I can check for if it is equal to 2, then that would be the answer. But my answer, this method just returns Boolean, either true or not. So I'll hold the answer in another variable here, private lowest ancestor value or lowest ancestor node equal to null here, and this one is a type tree node. Okay, lowest ancestor node would become what is that? Current node, which is node. Okay, so current node will become lowest ancestor node when it is equal to 2. Yeah, in this case, both were on the either on the left side and the right side, and it worked. Let's check for another case where 5 and 4. Okay, for 5 and 4, answer should be 5. Here what will happen is, for 3, I'll come on the left, and then it will go to 6, so 6 returns false. And for 5, left is false, it will come on the right. For 2, again, it will go to the left will return false. And then right, for 4 itself is equivalent to Q. So this will return true. So left is false, right is true, and current is also, it's not equivalent to any of those. So this will return 0 plus 0 plus 1. So it will return 1 and it will return true. And for this one, for 5, left is false, but right return true. Right return true. Left return false, which is 0. Right return true, which will become 1. And then the current, present in current, node itself is equal to 5. Okay, so node is equivalent to 5, so this will become 1. So I'm checking present on left, present on right, plus present on current. It's equal to 2. That's why I'm assigning that as the lowest common ancestor. So yeah, and for this one again, we go to 3 at the parent. For 3, it won't be, only the left side is true. Right side cannot be true because there are no elements. So this will be 1. Only for this particular element, the sum of those will be 2. So I can return this lowest common ancestor value after passing here. So I'll have to return this lowest common ancestor node instead of returning this one. I just have to pass that recursive or execute that recursive method, and then that will populate the answer here, and I'm returning that answer here. This should work. Let's see. Okay, lowest common ancestor node. I named it as node. Forgot to edit it. Okay, so this works. Okay, this is working. Got it. So now let's move on to this one is done. So we are done with the lowest common ancestor. Now convert sorted array to a binary search tree. So now we are given a sorted array. Okay, -10, -3 sorted array, and we need to convert it as binary search tree. So there are multiple ways with which we can convert a sorted array into a binary search tree, but they are asking us to return any one variant of it. So let's see, in this way, in this example, for example, usually sorted array means it will be the in-order traversal, right? So in-order traversal means, what if we take the first element as the root? If we take the first element of the as itself as the root, then all the other elements are greater than the first element, right? First element itself as the root, all the other elements are greater than that. So all the other element will go to the right, become the right child of the first element. So second element, if we take again as the next right child, so it will become like a linear structure, which is like a linked list. We don't want that, right? That is also a valid binary search tree, but we do not want that. To make it like a more like a even or balanced search tree into a binary search tree, they are asking for a binary search tree only. But here given an integer array where the elements are in sorted order, convert it to a height balanced search tree. Here they are asking height balanced. Height balanced means it should be at least the depth of the two subtrees of every node never differs by more than 1. So yeah, like if we compare the depth of these two, it should not differ by more than 1. Like if we compare these two, it is not differing by more than 1, even though there was no element here. If there was only one element, then also it differs by 1. So it should be fine. Of the two subtrees of every node. Okay. Two subtrees of every node should not differ by. So two subtrees of every node means two subtrees, like two subtrees. This is one subtree. This is one subtree of this node. For this one, this is one subtree, and this is one subtree which doesn't exist. So that is differing by 1, right? So 1 is fine. It should not be more than that. So it will be like a binary search tree, how we determine binary search tree. So what we can, if we want to make it like height balanced, then we can select the middle element as the root first, and then we can traverse, like we can use all the left side elements in order to build the left side tree, and we can use all the right side element in order to build the right side tree. And again in this one we can do it recursively. Like again the middle element we can take and we can build the left side. In the same way we can go ahead with that. So how should we proceed? Let's define a sorted array to binary search tree. Nums comma. Let's start with 0th index and nums.length -1. Sorted array to BST recursive method. So if this one is also returning the tree node, and then we can mark it as int start int int. This is nothing like solving just like solving the or finding an element in an array using a binary search. We divide and conquer there, right? In the same way we can keep dividing. As I said, once I get the middle element, I'll use all the left side elements in order to build the left side tree. and I'll use all the right side elements in order to build the right side element, and I'll follow the same procedure again. So what I can do is, if start is greater than end, then I'll just return null, or else I'll take a middle element, which is start plus end divided by 2. Once I have that, I'll create a new node. So I'm creating the new node with the value in that middle index. Once I do that, I'll have to build the left side tree and the right side tree. So node.left will become equivalent to, I'll call this recursive method again with the same nums, and the index should be, so for the left side, in order to build the left tree, the left would remain the same thing, but the right would become mid minus 1, because mid I have already used it to build this particular node. So now I'm building the right side tree and assigning that to right. So once whatever the node this one will return after building the left side tree, I'm assigning that as a left, and whatever the tree that is this one is building, I'm assigning that to right. For this one, start would be mid plus 1, and then end would be whatever the end it was while coming to this method. And after this is done, I'll have to return the node as it is. This should work. Return. I am calling it with recursive method. I'm returning. Okay. So if we see these cases, okay, this is working. It's fine. So these were like medium problems, and but except for the lowest common ancestor for a binary tree, not for a binary search tree. For a binary tree was easy. Binary search tree was easy. Binary tree was a bit tricky. It doesn't come out of the intuition. If we haven't seen the problem, it's not easy. We can solve it. It would take time though. So yeah. So these are done. Let me know if you have any question in this part, in this section. Post it in the comments. I'll get to that. Let's look into these problems in the next section. I'll take a short break before that. Thank you. Okay, let's get back to the problems now. So I'll be solving mainly these three problems, and if time permits, I'll go with another one, which is a balanced binary tree. Um, so first thing is serialize and deserialize a binary search tree. This is one of the lead code 449 problem. So I think most of these are also like medium or like close to medium. So yeah, this is medium. This is hard, but we are not going to solve it using the hard way. We like using tree, we cannot solve it in the most efficient way. There is another approach, I guess, but we will solve it using a tree set, which is one of the efficient methods. And the balanced search binary tree, this is easy one. So yeah, let's start with, but this is not easy as such actually. There is a top-down approach and there is a bottom-up approach as far as I know. The top-down approach is not so efficient, so that is easier to implement, but it's not the most efficient. But the bottom-up approach is not very intuitive, but yeah, that we can solve. We can look into that approach as well. Let's look into serialize and deserialization of binary tree. So in this one, as we know, serialization means converting any data into a textual format or the string format. Textual means into a string format. And then also deserialization means if we are given that string, you should be able to get the original data, whatever it can be. That is serialization and deserialization of a binary search tree here. So if a binary search tree is given, I should be able to convert it to a text format, and then I should be able to, if the text format is given, same text format is given, I should be able to convert it back to the tree. So there are both the methods. So whatever the output I give from serialize, using the same output, I should create a same or create the same tree with the same structure, not exactly the same with the same IDs, but it should be a kind of clone of that one with yeah. So let's see. So first thing is I usually use pre-order, like pre-order or post-order traversals are easy to reproduce. Like if we get it in that format, it's easy to convert it or reconstruct the tree. In order to get the pre-order, let's see a few examples if they have given. Okay, in this one only, case one, case two, yeah, case one here. 2 1 like this in this tree, the pre-order traversal is current node, next node, and then the following node, 2 1 and 3. So for this one, whenever I encounter a null, I'll store the null value also in order to like demark the like if it's in the child node or the uh, uh, like in I need to like if this tree is given. So this is a bit easier. So let's say some other example here. Let's say, for example, this tree, if this tree was given, so the same elements is given, I can construct it in different formats as well. Like if 9 was given, 9 comes before 15, then 9 could have been an immediate right child of 7, and then 15 must have gone to the right side of 9, and then 20 as the right side of 15. So that could, I mean, the same element can result in different versions. So the order also matters. So what I'll do is basically what we will try to convert it into this format, whatever the format they are giving in the question, close to that one. So let's check this one in the serialize and deserialize. First thing is pre-order output. So that would be a list of integer pre-order output. So while how to convert it up to the pre-order input. So we have done this many times. Pre-order, and then I'm passing the root node here. And let's add this also here. I don't have to mark it as pre-order output. Pre-order is enough. pre-order. This method, I'll name it as pre-order traversal. This one is pre-order. Okay, and I don't have to declare it again. Okay, so now I should define this method. And that should return a string for me. That should return nothing. It should just traverse and populate in this particular list. So here I'm going through this. If node is equal to null, then I should store that also. If node is equal to null, preorder dot add null, and then I'll return. If node is not null, then it will be like the order of current, left, and right. Current means I'll just first add the current node to the pre-order list. So that will be node.value. And then I'll have to call this iteratively to the left node and the right node. So node.left. Sorry, call this recursively. I'm getting confused today. Call this recursively to the left node and right node. So that will be added in the same order. Once I get this one, once I get this one, the values will be populated in this pre-order. After that, what I can do is I need to return it. So return it in the string format. String format means all of them should be separated by a delimiter or something. So let's make it as private static final. Let's make comma as a delimiter. And then so in this format, we have Java stream methods in which we can just write it in a single statement rather than writing a looping statements for each of those separately. So how does that go? Pre-order dot stream dot sorry dot I think it will have to map to string dot value of, in the string there is a value of static method, and then I need to collect all of those as a string joining by comma. So collectors dot joining, comma is the delimiter. Okay, this is a bit confusing. I'm not sure if it will work in the first. And I need to return the same string. Let's see if that works or not. Let me know if there is any problem with the voice or anything in the streaming. Let's see if this one is working. Public static final, and this is a string. Okay, so output is 2 1 null null 3 null null. Okay, so this is representing this tree, basically what we had. 2 1 and then null and null are its children, and then a 3 and then null and null are its children. So yeah, this is working as expected. So let's get to the deserialize part now. In deserialize, now we have this string in this format. So now we need to convert that same string into a tree and then return the tree. So first thing is, if okay, so I need to split the string into separate elements first thing. So what I can do is string of data values what I can do is data dot split by delimiter, which is comma. So that should give me the values, all these string as a separate ones. And then now I'll convert that to the, I'll deserialize that. I'll do that recursively. And using the same data values, instead of data values, let's make it as a new array list or a linked list. Okay. And it's a list of string now. And this should return tree node to me. So here, let's check from this one. So the first element should be in the pre-order traversal. The advantage is we can traverse from left to right. We don't have to traverse from the middle or anything. So the first element should be the root node, and then we will go to the left side, and then we will go to the right node. So if it is root node, then it will be like tree node current would be equal to data.get of 0. So data.get of 0, which is like, I'll use that as a value while defining a tree node. Data.get of 0. So that will be the current node. And then I need to remove that particular node. And then I should use rest of this list in order to build the subsequent part of the tree. So current.left will become, before this one I should do data.remove 0. I'm removing the first part, and then current.left will become equal to, I'll call this method again with data, and I'll call the same method again to construct the right part as well with data. And while building the left also, again it will take the first element and build a tree node, and then it will delete the first element, and then it will try to build its left node, which has null. So I should address the null values as well. If data.get of 0 is equal to, here it's not actual null value, but it's a string with value null, because this was serialized into a null string. Then I'll just return it as null. So, and then I should remove that as well. First value before returning data.remove 0. Okay, 0th element. So what will happen is, first element it comes here, it builds a current node as root, and then it will remove the first element and it will try to construct the left one. And for the left one, again it will construct a node with 1 here, and then it will remove 1, and then it will construct its left node. Its left node is null, so it will current.left will set to null once left is set to null. And then once right, again it's another null. One right of 1 is also set to null, and then it will come back to the original one, like 2 like 2's left child was built, which is 1 and 1, and then 2's right child, that has to be built. So that will take the next element 3. It will construct the node with for the 2's right, and then again it will try to build the construct the node for this one. It added the element and then removed the first element, and then its left should be built using null, and its right should be built using null. So null, left child is null, right child is null. So we have forgotten to return the current node as well. So once we build this, we should return the current node respectively there in all those in all the recursions. Okay, let's run this and see. Okay, so the problem here is all this I serialized it to string format. Now I'm trying to, like here I got string dot value of for all those integers. Now I should convert that back to integer values. So instead of using the string, so how can we do that? There is integer dot parseInt or integer dot value of. Okay, so this should, I think, return statement here. Okay, I should return whatever is returned from this one on the original root node. Okay, probably the equality operator should be equals in string, in Java string, instead of checking equal. So it was not going to this one. So whatever the null, I was trying to convert null as an integer. So I knew that this case is not handled. That's why it was coming out to here. So now since I made it as dot equals, it's handled here and I'm returning null. It's never reaching the statements. So let's submit this one. Okay, so this one works. So we are able to convert, serialize and deserialize a binary tree. So that is done. Binary search tree iterator. Binary search tree iterator. So this one, so in this one, like there are a couple of things we need to keep in mind. The same problem exactly can be solved using, like we can define a, like here the question is implement a binary search tree iterator class that represents an iterator over the in-order traversal of a binary search tree. Iterator over in-order traversal. In-order traversal means whenever I initialize the binary search tree iterator, it should point to the 0th index. And whenever someone calls this next method, it should start giving the 0th indexed value and then go to the next one. So it should go to the root and then it should go to the first element in the in-order traversal, and as and when I call, it should keep iterating to the next elements, and whenever has next is called, it should just return true or false, stating that the next element is null or if there is a value. So how can we do that? There are two ways. One way is very simple. We can convert it into an array format. Once I have all the in order values in an array, implementing the next and implementing the has next is easy. We can use the arrays iterator only, or we can implement it by ourselves only. Also, like by removing the element that we already provided, or we can just keep incrementing the index and stating that. Otherwise, but in order to do that, like if we do that, whenever we have an insert method, if we had an insert method here, if we have to insert something into this BST iterator, that would have been expensive, because in an array, if we want to insert, in order to insert it in that particular space, which is sorted, it would take O of n, because we need to, in the worst case, we need to move n elements to the following positions once we want to insert it into a particular location. But in the binary search tree, with the property itself, it will be sorted and it takes O of log n in order to insert any elements. So how can we achieve this one? In order to get this, let's initialize it as a binary search tree, and we can use a um, supplementary stack, as we did in one of the problems, I think, to find the successor. uh, in order successor. I think in order to find the in order successor only we used it. So we can use the use a stack, and we can use a controlled um, traversal using that one. So that way we should be able to simulate an iterator methods here. So let's go ahead with that and see. So let first thing is I need to initialize the stack is what I'm using here. Stack of 3 node, and I do not have to iterate all the elements beforehand or anything. Node easy. Okay, let's initialize that stack. Once I have that stack initialized, whenever I have to call the next method, what I can do is basically here. Um, so here for every method, like everything I'm calling, I need to get the leftmost of, yeah, like how did we do the successor? In the successor method, we were seeing the leftmost in order method. So let me see. Okay, we have a stack first thing, and then we should get all the leftmost of its element into the stack. That's what we did in while we were finding the successor. And then once we find that, like we should see if the in the after we find the next also. Okay, let's get this one first out of the way. Once we have the stack ready, while root not equal to null, stack dot push. Okay, so once I have this one, like I have, so I'm pushing all the leftmost elements. So now I have to, now the iterations has to recoil. So the way we had explained for the successor. So let me see here, like how I initialized it. I initialized a stack, and let's say for this example, sorry, this example was not visible. So in this example, there is a 7, and 7 is not the first element. We know whatever the leftmost element is gotten by traversing to the left. So this is like traverse to the leftmost element by tracking the path in the stack. So I did that. So now I have the stack ready, with which I can retrace the path to this root as well. So I have the path from root to its leftmost element. So once that is done, whenever someone asks me for the next element, what I should do is I should, first thing is uh, topmost element. Let me take it as current element. Then I'll just pop it from the stack. Once I pop this element from the stack, this element can have a right child also. We should mind that as well. So if this element had a right child, that means it is greater than this element, but it is less than its parent, its immediate parent. So that means this whatever is on the right element, that would be the next element it should return in whenever we call next. So that means we need to get that prepared as well. So in order to get that prepared, while um, we did the same thing here also. We can uh, separate it out into a different method. Private void leftmost element, leftmost traversal. Okay, so here tree node. Okay, so what I'll do is, and then I'm passing this. Okay, we don't have to pass the stack, it's available everywhere in this class. So yeah, so what I did is, while node is not null, I'm pushing the node leftmost values of the node into the stack, and I should do the same thing here as well. If current dot right not equal to null, then what I'll do is I'll call the same method leftmost traversal on this current dot right method, current dot right node. Once that is done, I call the leftmost traversal for the current dot right node. So I can return whatever I stored here, right? Current dot right not equal to null. Okay, I traverse to the leftmost node here, whatever the leftmost node, and then I can just return, and it's asking for the integer value, current dot val. Okay, so this should return the next value in the stack. And as next, for this simply we can just return if stack is empty or not. If stack is empty, then we do not have any more to traverse. If not, we will be traversing. Okay, there is an empty stack exception. Okay, so what is the scenario in which it is failing? Let's see. So okay, I'm pushing everything to the left, all the left elements to this one, and I have defined stack in the iterator, and yeah, it looks good from top level view. So what is missing here? Right, failing in the next method here. The next method. So anybody has any clue? Yeah, what might be going wrong in this? Seven, 13, 15. So let's see this. This is the table. 7, 13, 15. 7, 3, 15, sorry. So 3 is the left child. Let's use debugger since it's been a while in the live stream. I cannot use my mind effectively to troubleshoot without the debugger. Okay, it's showing empty stack exception. Let's do this thing. Okay, stack.size is 0. That's why it is. That's why I'm not able to pop the stack here. So why it is 0? If node not equal to null. Oh, my bad. I removed from here that logic. I forgot to call this method in the BST iterator. I had written it in place there, and then I moved it to this method, and I forgot to add it back here. That should work now. Now it works for that case at least. And then true, true, false. Okay. Okay. The mistake was for has next, I was returning if stack is empty. If stack is empty, it means it does not have next. For has next, I need to check if stack is not empty. So corrected that. Now it's working. Let's submit it and see. Okay, so this one works. Okay, let's move on to the next problem, which is which has a different optimal solution as I had seen, but we are going to solve it using a tree approach, which is uh, which we are familiar as of now, but we can treat the other one as out of scope for this session. I can address it later, and we might not even have to look into that, but this will make us familiarized with the tree set using the Java library and how we can use it in the real world also and in these LeetCode problems as well. So let's look into this one. So here, for example, the question, first understand the question. You are given an integer array nums and two integers, indexDiff and valueDiff. Find a pair of indices I comma j such that I is not equal to j, and then the difference of I and j is less than or equal to index difference, and then the difference of values stored in I and j should be less than or equal to value diff. Okay, I know it's too much to grasp in that time, so let me explain. So they have given a array. Okay, as usual, it array of numbers, and then they have given two more numbers. One is index diff and one is value diff. What we need to find out is index diff. Index diff means we index diff is 3. So there we should find out two elements or two values in that array such that their index difference is less than 3, and then their value difference should be less than whatever the value difference. So that means um, here index difference is 3. So in this case, one is at 0th index and other one is at 3rd index. So the index difference is 3 at most, and then their value difference is 0, right? So less than or equal to value difference, whatever it is given here. So their value difference is 1 minus 1, 0. So both of this satisfies. So that's why we return it as true. If there was no one here among these plus 3 index or minus 3 index from this one, then we couldn't have achieved it. Or else, let's say if this was, it was 2, 1 2 3 2, if that was the array, then also this satisfies, because within the index difference of it doesn't have to be exactly equal to the index difference of 3. It could be less than or equal to index difference, and also value difference doesn't have to be exactly equal to this one. It has to be less than or equal to the value difference given. So here in the second one, let's say here index difference is 2, value difference is 3. So let's say uh, here index for 1, index difference is 2. So next two elements, let's see, in the next two elements, let's treat that as a window. Is there any value with value difference of 3? No. 1 plus 3, 4. There's nothing less than or equal to 4. For 5, for let's say plus 2 index difference and minus 2 index difference. Minus 2 we are already seeing it, so we don't have to. Plus 2 index difference, 9 and 1. Both are of index value difference greater than or equal to 4. For 9, again 1 and 5, both are of value difference greater than or equal to 3. And for 1, again the same thing. For 5, it's the same thing. So we don't find anything satisfying this conditions within the window of 3 elements. So I'm returning it as false. How can we solve this one? One approach to solve this one is the same way, using the windows in the array. We can keep a window of 3 elements, and then we can within those 3 elements we can see if there is anything satisfying that criteria. But what's the downside of that approach if we are using an array, and if we are trying array or a set, and we are trying to figure out if there is a value like that? The downside is that in order to find such value, or in order to do the comparison, we need to compare it one by one. So if we have to compare it one by one, then the worst case is like it could be O of whatever the value here. If the index difference is 2, O of index difference. We need to do it as like, if n is the total number of elements, n times we need to compare with O of index difference. Let's assume it as k, n times O of k. But what if we maintain it in a sorted structure, like a tree set or something? Let's say if we maintain it in a sorted structure like tree set, then every comparison we need to do, we can find the element appropriately in log k, I mean log of index difference, but the n will be the same. We need to do it for each element. So it would be n log k instead of n into O of k. O of nk, it will be O of n log k. So that is quite a bit of saving in terms of the runtime. Let's see how we can implement that approach. First thing is tree set. We need a tree set of integers, and usually I initialize, while defining, I initialize it with like a generic generic types like set, or if I'm initializing a hash map, I'll just define it as map, or hash set, I'll define it as just a set and all. But here I'm using specifically tree set. I'll explain why. So there are a couple of methods which are exclusive for tree set. In order to use those, I'm initializing it as tree set. So let's see, while we have to keep iterating through each of those. So in order to iterate through each of those values, let's do this. For, and we need the index also in order to compute the index difference. So let's iterate using this indexed for loop. So once we do this, our ultimate goal is to add it to tree set. Okay, let's make it as tree set. Tree set dot add nums of I. And another thing is, we do not need all the elements in the tree set. We need the elements which are appropriate for that window itself. So what we can do is, if tree set dot size greater than k, or it should be greater than k plus 1. So if it is greater than k, then we can remove that element, remove the older element in this one, not all the element. Tree set dot remove. So here, now let's say I need, like, when I came to 9, I should just compare with 2 elements, right? When I come to 1, I should compare it with only previous 2 elements, not with the third element. So I can remove this element. So this is the index 3. So index difference is 3 minus 2, 1. So I should have only till 1. 3 minus 2, 1. Okay, I should have only till 1. I should remove the 0th index. So that means I is 3 minus 2. 3 minus 2 is 1. 0, 1, 2. Okay. I minus 3 plus 1. Okay. So I cannot remove directly by index in the tree set. I can remove by value. 0, 1, 2. I hope it's correct. 0, 1, 2. 2 minus 2, 0. Okay, I already compared and I removed. Basically, okay, let's see. Next term. Next thing is, I need to see here, that is the adding part, adding to the set. So now I have the set, I have all the elements in the set. I need to figure out what is the field value, or which is the element. So let's say int successor, immediate successor. So I need to figure out an element such that in this one, in the tree set dot ceiling of which value, of nums of I. So once I have this value, and also at the same time, I'll explain this one. Tree set dot floor of this value. That will be given by this one. So here ceiling means how I'm thinking. Ceiling means, let's come to this example here. So ceiling means current value is 1. Ceiling means next immediate greater value within that range. Next immediate greater value after this. And floor is next immediate lesser value after this one. Next immediate lesser value, and this is next immediate greater value. So I'm calculating that because I need to find the value difference also. If the value difference between them is less than the value difference mentioned, then I can return true. If I don't find any such conditions, then I'll have to keep iterating and look for satisfying that condition. And here, this one satisfies the index difference condition, because in that tree set, I'm just managing only that many number of elements all the time. So if it satisfies, it will be satisfied among only those elements. So here, once I find the successor, I check the condition. If successor, or how the successor is given. So if successor, um, so successor is less than nums of I plus value difference. So successor is the next immediate element, right? So if it is less than or equal to nums of this, nums of I are equal to also nums of I plus value difference, then I can return it as true. And for predecessor, if predecessor is greater than, there also be less than or equal to nums of I minus value difference. I think that should work. Minus value difference. Yeah. If it is less than or equal to, no, it should be greater than or equal to. Predecessor should be greater than or equal to nums of I minus value difference. Yeah. Then I can return it as true. So here in this case, I'm checking, let's say I'm at 9. I'm checking index difference is 2. So I have 2 elements in the set. Value difference is 3. I'm checking if the successor, whatever the successor I get, successor is, there's no successor actually. There's nothing greater than 9. So let's say for 5, for this 5, let's say, there is successor as 9 and predecessor as 1. So I'm checking if 9 is less than or equal to nums of I, which is 5. 5 plus value difference 8. So if 9 is less than or equal to 8, no, then I won't return true. And for at the same time here, predecessor is 1. So I'm checking if predecessor 1 is greater than or equal to nums of I 5 minus value difference 5 minus 3, 2. So 1 is not greater than 2. So I'm not returning this one also. So I'll come here and I'll just add the value and I'll keep comparing with the next one. Yeah, this should work. I'm just not sure about these methods, the usage of these methods. Let's see. I rarely use those ones. Okay. And then I need to return false if it comes out of this one without satisfying any cases here. Okay, if tree set dot size is greater than k. Okay, there's no k here, so which is index diff. Index diff we thought of as k in, yeah. So, and I is the here, this one, nums of I. Okay. Okay, so this one is given as null pointer exception. Ceiling object is returned as null. So this is returning an object. So instead of integer, let's consider it as integer, and then let's check for the null for that one. Not equal to null, and okay. Okay, so this one works. So this is returning an object which could be null. If we don't find any predecessor or a successor, for example, for 9 we didn't find any successor, right? In that case it was returning null. So let's submit it. Okay, this one works. As I said, this might not be the most optimal approach, but this is the approach which is more optimal than using a plain list or a list or array list. So that is done here. So let's move on to the next problem, which is let's see. Okay, we are done with all these three: contains duplicate, binary search tree iterator, and serialize and deserialize. So next thing we can move on to either see this balanced binary search tree or not. Like there is one question which is to find whether a tree is balanced or not. So let me see if we can go through that once. So balanced binary search tree. Okay. So given a binary tree, determine if it is height balanced. Height balanced means, as we mentioned the other time, I think we saw it in one of the other problems, I guess. Height balanced means the difference between the height of any two nodes of a parent should be less than or equal to 1. So the difference, so for this one, for example, the two nodes like the 9 and 20 are its two children, the height difference is, the height of this one is 1, height of this one is 0. So okay, it's balanced. But for this one, height of this node is 3 and height of this one is 1. So difference is more than 1. So difference is 2. So this is not a balanced tree. This is not a balanced tree. Height of this one is 3 and height of this node is 1. So difference is 2, which is why it is returning false. But here height of this one is 0 and height of this one is 1. So it is returning true in this case. So there are, as I explained, there are two approaches with which we can approach this problem, and it is given as easy. The first approach is pretty easy. So all we can do is top down. So basically we will do certain recomputations here, not the most efficient way, but it's easy to code up using the recursion. So let's see how we can see if it's balanced. So let's go with the easier way first, the top down approach. Here what we will do is, if root is equal to null, then we will just return it as true. It is balanced. Otherwise what we will do is, if okay, we need a method to compute the height in this one also. Private int compute height. In this one, node okay. Once we have this one, if node is equal to null, then return 0. Otherwise return 1 plus math.max of same thing, compute height of node.left comma compute height of node dot right. So that would be the height of any node. So now if we have the height, let's see if compute height of root dot left minus compute height of root dot right, if that is greater than or equal to 2, or if it's greater than 1, then we need to return false. Okay, we need to, anyway, recursion, whatever the easiest problem, it's easy to make mistakes, so we need to keep patient and keep our mind composed and start looking into that pattern. So okay, I computed the height and that should return false. Otherwise, what we should return, if this is not all, these two are not satisfied, if it is null, then I'll return true. If the height difference is greater than 1, then I'll return false. Otherwise, I need to compute the validity of the uh, balanced validity for its immediate child nodes. So I'll return the is balanced for root dot left and is balanced of root dot right. Okay. So now I have this basic implementation. Let's see if this works. Okay, this one's working. One null, two null, three. So use this test case. Okay, this one is clearly non-balanced, but I'm returning true. Why? So turn it as -1. Yeah. Okay. So I think one mistake is I'm just computing if this one minus this one is greater than 1. It could be the other way as well. This one or this one also should not be greater than 1. So root dot right, yeah. So in that case, what I'll do is math.abs of absolute value of the difference I'll calculate. So in that case, it will be, yeah. So now it is satisfied. Okay. So this is the simplest version, but in this version, what we are doing is we need to, for computing the height here, we are going through each node, and we are recursively going through each node and computing the height for left and computing the height for right, and we are again calculating is balanced of node dot left and node dot right, so it will again go in the same path or traverse in the same nodes. So how can we make it more efficient then? It is non-intuitive, but it's bottom-up approach. So this is like top-down. I'm comparing for the topmost element. If the height difference between the its left and if its right is greater than 1, then return false. Otherwise, otherwise just see if the subsequent nodes are balanced or not. And even for that one, I'll compute it the same way. So now let's compute it using another approach. Which let's comment out this whatever we already coded recursively. So for this approach, basically all we need to do is we need to check, like while returning, like we will traverse from top to bottom, and then while going from bottom to top, we will be returning the height of the node with with the information that whether those nodes are balanced or not. I'll just return the height of those nodes as well. So in this case, um, for example, in this case, in this tree, we are given in this tree. Let's see. Yeah, in this tree, for example, we are given. So why it's showing? Yeah, in this tree we are given. Basically, when I say that, okay, when I ask individually for one, the left tree of this one is balanced, height balanced, and the right tree is height balanced as well. But when I see the difference between the left tree and the right tree, then I know that, okay, it is not a balanced binary tree. So I just don't want to know if the left tree is balanced and the right tree is balanced. I need to know left tree is balanced and right tree is balanced. With that, I need to know the height of those individual ones. So here, for example, the height of the left tree is -1 because it's null. And the height of the right tree is 2 or 1, I guess. 0, this is 1, and for this one it's 2. Yeah, it will return 2 for this one, right? So height of the right tree is 2 and height of the left tree is 0. So it will become, I'll have to compute the difference between those at this level also, and I'll return false. Otherwise, I would have returned true if I don't compute that. So that's the whole reason here also I'm computing if the height difference by calculating the height with this statement. If I didn't do this and if I just do this thing, then it would have missed these scenarios, as we can see here. If I had not done this, yeah, there's no way we can know everything is returning true. Yeah, everything would have returned true in that case. So yeah, that doesn't make sense. We need a terminal condition. So this is the terminal condition here. So again, it will throw an error. Yeah. So once this is done, let's come back to this approach and see how it fares. So in this approach, we need a structure in which we can hold the something like class tree height and int balanced. So it will return both the information while coming up from the top. So if we get that, and then let's define a constructor also. Let's mark it as tree data. Yeah. So now and it should be Boolean balanced. Okay. So these are the two important pieces we need. That's why I'm adding those things. So first height is equal to h, and then balanced is equal to b. Yeah, it feels bad to actually name it this way. Let's mark it as okay. In order to remove confusion, we can mark it this way. Yeah, got it. So now once we have that, so we need another function. So this will return a tree data. So within that tree data, I should check if it's balanced and then return that one. So private. So now every node from the bottom up, when they are returning, they will return the tree data, including the height as well as the balanced both. So we don't have to keep going again and again. So now we have tree node. Okay. If node is equal to null, then what should I return? First thing, if node is equal to null, then I should return new tree data. -1 is the height. Height is the first value, right? Yeah, height. And then it is balanced. Yes, it is balanced, which is true. So I'm returning that. And what if it is, if node dot left, let's compute for this one. For the recursive function of left and right, both we need. So in order to do that, let's calculate node dot left and node dot right. So left data is balanced of, okay, node dot left. And in the same way, I need the right data. So once I have the left data, if left data dot balanced, if it is not balanced, then I can return immediately. If one of those nodes are not balanced, I can return immediately new tree data. And height does not matter when the balanced is returned as false with one of those things. So I'll return it as balanced is false, height is -1. Height doesn't matter basically. That's why I'm returning random height. And here, if the right data, okay, if the right data dot balanced is not true, then I'll return it as again false only. Next thing, if left data dot height minus right data dot height, whatever is passed, is less than or equal to 1, less than or equal to 1, then I should return new tree data of height. What would be the height of that one? Height of this one would be mat.max of either of those heights. And then they both are balanced means, okay, it should be balanced. So I'll return it as true. If none of these conditions, if these conditions are not satisfied, I mean, then the difference is more. That means I should return it as false. Return it as false, which is returned in this format. Okay. So here, I think again I'm doing the same mistake. So height could be either of them can be greater. So math dot absolute value of this one. So this one should work. Let's see. What else? And another thing is here the height of this one. This current node is if the left node's height and right node's height, maximum of those heights, and then I need to add one also to this one. Anything else? Let's check this. Okay, there is not. Okay, this is not int. This is tree data. Okay. So, okay, these values. Okay, so it's working overall. So yeah, looks like we completed all of this. We added one more problem. Problem 12, which is balanced binary tree and 110. Approach using top-down and bottom-up approaches. Bottom-up recursions. Okay. Well, in this one we will be traversing through each of those. Yeah, so that should be it. That's a wrap. So this pretty much covers every complexity level of binary search tree, and a lot of those questions appear again and again during the interviews. I cannot think of preparing more for binary search tree alone. If there are more questions, we can solve it using this, using the knowledge of whatever we saw today. So this is the basic that we need to solve any type of problem that are asked in the interview. So this is a must prepare for any interview. And beyond this, if we want to solve any problems, we can solve it. And also it's easier to solve now since we are in the mode of binary search tree, and we know that for every problem that we are solving, we are using the binary search tree and the principles. But in the interview, we would not have that context. We might not be asked to solve everything using binary search tree or a tree set or anything. We need to think on the spot there which data structure is more appropriate, what properties of that data structure we need to use, and hence come up with the solution. So that is a bit more challenging. I saw many questions today, and people were interested to ask more questions. And yeah, anybody have any questions or any doubts, and if they want to schedule some time, also feel free to schedule time. I'm here to help. The only reason why this channel was created was to help in a larger scale. So I'll be happy if at least one person is able to clear clear a good interview, or if one person is able to get a better package than what they were targeting, then it's a success. So yeah, I think I'll keep continuing this one. I'm having fun and I'm learning with all of you guys as well. So let's hope we will have the have a successful journey after this. Let's see. I'll be learning more of things, like not just limited to data structures. I'll branch out to different things once these things are done. So yeah, let's see how it goes. If you have any questions, feel free to reach out on my email that I'm posting now, or you can drop me a message or in the comments as well if you have any questions. I'll make sure to address those or explain it. Thank you very much. Have a good night. Who all are in the stream now? So please drop me a message as well. I would know who was there. Thank you.